We'll be able to put the orange one up and actually compare it to the distribution. So the big takeaways right now, the sampling distributions take on basically a bell shape. A little hard to see green there. So we get a bell shape even when the original distribution wasn't bell shaped. That's kind of rad. And the highest parts of the sampling distributions correspond to the average in the population distribution. I think, Cassie, you hit it on the head when you said, this is great. That means we don't have to measure everybody in the population. That's why we care. That's why we care. Now, here's why we're concerned. We're concerned because, yes, these are bell-shaped curves. For example, blue over here. It's a bell-shaped curve. And the highest bar contains the average. The problem is there are 40 different studies contained. Each one of those 4 roll groupings is like a research study that's done at some university. So it's the one that tests Advil for headaches or whatever for whatever. So you get one of those. So yeah, 16 of the 50 caught the average perfectly, but that means 34 didn't. The other 34 missed it a little bit. Half were too high, half were too low. See what I'm getting at here, friends? So 17% are too high, 16% are perfect, and 16% roughly are too low. So a third, a third, a third. Does that concern us? Does that concern us that we only hit it basically within a half of a unit 16 out of 50 times or 32% of the time? No. Not so much. How come, Cassie?
I feel like it's expected.
Oh, it is. Well said, sister. Well said. It is expected. But here's a question I have for you, though. Here's a question. That's a great answer. Perfect.
If it were drugs and it was a migraine, I sure as heck would, I'd be pissed.
And right there, Athena, is the suffix to Cassie's statement. Cassie's statement is correct. It's expected to have the variation in the sample. But Athena's point is awesome, too. If it's a migraine, and I want to know I can say my migraine is going to be reduced by 30%, I will not accept 15%. I want 30%. Love it. Love it. So the question is, how do we deal with that? Well, let me ask you this question first. I'm going to back this up. I'm going to back this up a smidge to the blue. There's the population of the blue dice. Notice it has a standard deviation of about 2.6-ish, 2.65. What do you think the standard deviation of this sampling distribution is, numerically? And if you can't give me a number, say either more, less, or the same. What do you think the standard deviation of this distribution is? More, less, or the same? Think about it. More, less, or the same? Remember, it's bell-shaped. You use that to your advantage. What do you think, Corey?
7 to 9.
What are you doing 7 to 9? I love this.
That'll be one standard deviation.
Oh, I love what you're doing, Corey.
It's about 68%.
So what Corey's doing is he's saying, oh, this is a bell curve. If I imagine the areas here, and I pump out like that, about to hear where you went, 68% of the data? You actually counted it, weren't you?
I was counting it because we have 50 samples, so I just double the number and get,
Nice, you get 100.
32.
So you said, let me get 30,
About
34,
32,
right?
yeah.
Right-ish, somewhere in there, right? So roughly these right here,
Right.
that's 68% of your data, isn't it? That's 68%, roughly. We're going ish here. That's 2/3 of your data. That would be one standard deviation from average, correct? So, if that's one standard deviation, that means one standard deviation goes from 7 to 10. Well, remember what that means. That's x bar plus s down to x bar. Oh, it went too far. It's right here. X bar minus s. Well, if that range is 7 all the way up to 10, that's a distance of 3, but that's actually 2 little s's, isn't it? One up and one down. So if the whole distance is 3, what's one standard deviation? 1.5. How does 1.5 compare to 2.65? It's less, isn't it? So the standard deviation of this distribution is less than the standard deviation population. I think this is good news for us, isn't it? Because now we have less variation in our sample than in our population, which means we can say, oh, we can get more accurate, or more precise, I should say, in our result. Fair? Okay. Guys, keep going with it. Keep going with it. Let's go to the yellow curve here. That's the yellow sampling distribution right there. Here is the yellow population distribution. What do you think? More variation in the sample? Less variation in the sample?
Less.
Definitely less. You guys commented the outliers dropped off, right? If the outliers drop off, that means the data is spread out less, which means the variation is less by definition of variation. Is that fair? Good. Let's go to green. Here's green. What do you think? More or less variation?
Less, I've already looked at it.
Definitely less variation. We've lost the outliers again. We'll jump over Jesse for a second and go to red. Red's a little bit trickier. Red's a little bit trickier. More or less. Once again, it's less. It's covering less distance on the horizontal axis. The population data goes from 6 to 12. The sample data goes from 7, barely, more like 8, up to essentially 11, barely catching 11. So again, your variation is less. So check out these 3 things we've got so far. Number 1, the bell shapes pop up. That's freaking cool right there. The fact that you get bell shapes is awesome. Number 2, what was the second cool thing about them? The bell shapes themselves? What was cool about the bell shapes? That we were like, wait a minute, that's kind of cool.
They mirror? No.
Well, you get the symmetry, and what's the symmetry point?
Average.
Yes, the average of the population is at the symmetry point. Yay, that's fantastic. And what's the third thing that answered Athena's question, or dealt with Athena's question? How is the variability in the sample related to the variability of the population? It's minimized. Now the question is, can we minimize it even more? Next question, we'll get to that. Can we, because what this basically says is, as Corey said, 2/3 of our data's averages come in from 7 to 10. Well, a difference of 3 might not be, except that might be too wide. Can you make 68% of the data come in between like 8 and 9? Or 8.5 and 9.5, or something along those lines? We'll answer all these questions. Look at this, look at orange. I love ending with orange. Look at this. You remember what the orange distribution looked like, friends?
No.
That
Oh.
is what the orange distribution looked like. Horribly bimodal, completely asymmetrical, and then you take a sample of size 4. Oh. And look at it.
So does
Why
that
does
mean
the
that
force-
these aren't very accurate then?
No, it means they're super accurate at targeting what? Yes, the average. We are targeting the average. The sampling distributions are perfectly mirroring the average. No. What Cassie's saying is, wait a minute, you're losing the shape of the distribution. Yes, you are. But very often, you don't really care about the entire distribution, just the center of it. Very often. Is that fair, Cassie? Great point, by the way. Ish. Now, I want to revisit both Cassie and Athena's point from earlier. We did minimize the variation. Ideally, I would want to look at this sampling distribution right here and go, the average is 7. I can't do that right now. I can say the average is somewhere in those tallest bars. That's the best I can do. It'd be awesome to get a little more precise with our results. Well, ish. Yes. Well, ish right now, in general, we're going to have to do something else, Cassie. So I would like to answer your question both ways, using Excel, but also addressing your point as to how to do it without Excel and data itself. So check this out, friends. Let me shut this down for just a sec. Is that running? That's running, yeah? Okay, let me pull this down. So what I want to do is I'm going to re-explore the blue distribution momentarily. Okay, I'm going to re-explore the blue distribution, which is here. Wait a minute, I need to be, Excel, that's right. Okay, friends, that's the blue dice. So you guys that did the experiment on the blue dice, that's what your dice look like if you blow them out. Those are called dice nets.
Right, we roll them.
If you were to pull up the sides, flatten them, that's what you would see. And this is what you guys use to figure out how to do your sums on your dice. Now remember over there, the average of the blue dice is 8.2-ish, and the standard deviation is 2.6-ish. I put WLOG, remember what WLOG means? It's okay if you don't. I've used it a couple times in passing. Without loss of generality. What that means is I'm looking at the blue dice. I could have just as easily looked at orange or green or red or yellow. I just decided to do blue because I had that first in my PowerPoint. So in other words, what we're about to discover here will hold for any of the dice. Any of the dice at all. Fair enough? I promise. You'll see why here too, Cassie. You've already seen part of it already on the board. That's okay. You should be skeptical. That's a very good thing to be statistically. Okay, here, what I want to show you is what is going on here. What I've done right here is I'm using Excel to roll your dice. Now the way I'm doing this is I'm a bastard. And I'll show you. Over here, up here, I hid the distribution up there in the top left corner with white. That's the actual distribution of the sums of all the dice. And then, because I'm a clever little SOB, each of these, look at that command right there. What it does is it randomly generates 2 random numbers between 1 and 6, and then it sends it to that grid and picks the random coordinates to find the random sum. So essentially, it's doing the exact same thing you guys did with your dice, but it's doing it in Excel. But the reason I did it this way is, see, there's 4 rolls right there. There's 4 rolls right there. I did this 1,000
And is
times.
this still just the blue dice?
This is just the blue dice right here, Cassie, but all I have to do to change it for the other dice, Cassie, is to go over here and change this row here and this column here to your sums, to your dice values. It would still be your distribution would show up. So what you're seeing right here, friends, is 1,000 4-roll grouping, so 4,000 rolls. And every time I press F9, it rolls it 4,000 more times. Now, does that curve look familiar to you? Does that curve look familiar right there?
Yeah, looks like the original one.
Uh-huh. Look at that.
Yeah.
There's the blue population curve.
Yeah.
Look familiar? It's the same curve with the proper-ish from your project 3. Every time you press an F9, you're reshuffling the dice and you're getting it. So what this tells us is that's the stabilized population, basically. That's the stabilized population. The only difference I did was I changed it to a probability distribution instead of a frequency distribution. Why? More on that in a second. It helps to see a certain point. So the most likely outcomes are 7, 9, oh my goodness, hello, are 7, 9, and 11. Didn't realize I started out with that, I apologize. Cool? So you're getting some wiggle. You're getting some wiggle, which is totally fine. Wiggle, wiggle, wiggle. That's totally fine. But they're stabilizing on their actual heights. Okay, so that's the original population. Next slide over. This is the experiment you guys just did on steroids. I took the exact same values, but I took the average of the 4 values in this column, and then I graphed all those averages on this bell curve. Oh, excuse me, I take that back. I graphed all those averages on that curve, and that curve turned out to be a bell curve. And you see, every time I do this, look at that. You see what's going on, friends? Isn't that freaking ridiculous? Yes? Notice where the tallest bar usually is. Where's the tallest bar? Usually. The one that contains the average. The question, where is mu? It's right there in the tallest bar most of the time. And if it's not the tallest, it's the second tallest. But it's never like the shortest. It's all right there. I just stopped randomly. I just hold it down and stop. Right there. Boom. It's again the tallest or the second tallest. I can't it's a little bit taller, I think. Tiny bit taller. So that's pretty cool, isn't it? That's pretty cool because we're catching the average about 14% of the time. Now remember what we said it was over here, about 16% of the time? Okay, that's not great. Excuse me, that was actually 30% of the time, but this is broken down a little more accurately, 8 to 8, 5 to 9. So put these two together, that would be like your bar. So roughly the same percentage, But this doesn't address the Athena's problem, because you got to remember, that's 1,000 samples, but one of those samples was this average down here, which is nowhere near the true sample, isn't it? I mean, the average is, excuse me, nowhere near the true average. The true average is 8. An average of 3 is a vast underestimate, just like an average of 11 is a vast overestimate. It would be really good if we could somehow mitigate the chance of getting those values. How do you think you do that? How do you think you make it less likely to get values out here? Now, this is an extraordinarily tricky question, but I think you know the answer to it because I think you said it already. Do you remember what we said? That the sample standard deviations on this curve was less than the population standard deviation itself? And this was a sample of size 4, where the population was drawing things one at a time. So what do you think we can do to make the standard deviation even less?
Draw more than 1?
Yes. Let's draw 9. That's this tab right here. Watch the curves. Watch the curves. There's 9. How is 9's curve related? How is it related to 4's curve? It's the same shape, Ashley. It's still a bell curve, isn't it? How is it different?
It's mushed.
Aha! Are you seeing any 3s down there anymore? Are you seeing any 11s up here? Now, every once in a while, you might see an 11. Oh, every once in a while, you might see this guy pop in. One of these guys down here pop in. But you're getting rid of those outliers, aren't
Closer
you?
to the one on the board.
Say that again?
It's a lot closer than the one on the
It is. Ready for this? How we get it even? Now, Athena, what we're doing is we're homing in on what you said about if I've got a migraine, I want less variation. I do too. So why don't we sample, I don't know, 16. Watch this curve. How's that curve related to the other ones? It's bell-shaped. How is it different?
Smushed more.
It's smushed more. Are you catching the percentages up here?
Oh, I didn't even look at that.
Look at the percentages. Look where the average is. The average here is at 14. This one's at 20. Now it's at almost 30. It's going up in the middle. Now it has to do that, doesn't it? If we're losing the tail, the middle has to go up because it's not going to be 100%. Fair enough? Oh, why don't we go to 25? Why don't we go to 100? You see what's going on here, friends? The more sample, the larger the sample size, the less variation that we've got. I wanted to do one more. I tried actually. I set up a 10,000 tab, a sample size of 10,000. You got to realize what that entails. That entails 10,000 rows going this way and then 1,000 going down. So that's what, 10 million data points? And I've never seen Excel vomit before. It was awesome. I hit F9 and went, phew! And literally like 5 minutes later it was like, bing! And like the curve showed up. And guess what the curve looked like? Guess what the histogram looked like? It was 1 bar, 1,000 high. Because they were there, we basically shrunk it down to this. You see what I'm getting at here, friends? So I figured you guys were going to wait 3 minutes for that to happen. So rather than see that though, I think what I want to do is I want to take a look at this. This is a little hard to look at first. But down here when I've got the bottom is all 5 graphs at one time.
Oh, okay.
There's your sample of size 4, 9, 16, 25, and last but not least back there is the 100. Now notice, as we change the data, they're doing a little thing, but do you see how they're getting taller as they go front to back, as the sample sizes go up?
Yeah.
And if they're getting taller, they're also getting thinner, narrower, thinner. I love that. That's fantastic. Now, what's cool about that is you guys are about 95% done figuring out what the central limit theorem is all about. Number 1, you recognize the bell curves. Hell yeah. Number 2, you recognize that the highest points of all the curves are above the category that contains the average. Hell yeah. That's also awesome, right? But what we haven't quite done is quantify how much narrower the curves have. So what I want you to do is I want you to look up here. This column right here is the average of all 1,000 sample averages in each sheet. That's a lot of data. So essentially, let's go back to the 16 here. Okay, these sample means all the way down. What I've done is I've averaged all of those. So I've taken the average of all those averages and placed that average right here. This is the average of all the sample size 4, sample size 9s, and so forth. What do you notice about all of these numbers, friends?
They're pretty close.
They're pretty close, and they're all pretty close to what? And that's what they should be close to because that's the average of the population. Fair enough? Fair enough. What do you notice about these numbers?
They're really different.
They're different and they're doing what?
Yeah,
They're going down, aren't they? They're going down. Does that correlate to what you guys said about the curves getting thinner?
Oh.
Yes! They should be getting lower as the sample sizes go up because the curves are getting skinnier. But now what I want you to do is I want you to quantify it for me. How much skinnier? Answer as a fraction. How much skinnier is 1.31 than about 2.7-ish? As a fraction. It's about a half, isn't it? Let's try another one here. 1.3, 1.34, 1.35, 1.3, they're all about a half, aren't they? How about this one right here? 0.86, 0.89, 0.87, 0.89-ish. Ish.
Third.
About a third, right? Call this 2.7, right? This is 2.7. This is going to be about 0.9, right? About a third-ish, about a third. How about 0.67? 0.67, 0.65-ish. About a quarter. About a quarter-ish. Good. Be brave.
Because it's just going down by 1 each time.
Careful. Close. So Cassie's saying this should be about a fifth, and I think it is. It's about a fifth. But then how about this one? What's this one here?
8.
Okay, 0.27 versus 2.7. 0.26 versus 2.7. 0.26 versus, it's a tenth. It's a tenth. Now, your job right now is to look at those numbers and to see if it's predictable. Could you have predicted, if I got the 10,000 sheet to work, what that value would have been for 10,000? If this was 10,000, what would that have been?
If it was 10,000, it would be like nothing, wouldn't it?
Yeah.
Basically, numerically, it would be 0.026. How the hell could I have known it would be 0.026? Why, Chris? Let me ask you a question. If this were 49, what would this be? If this were 64, where are these numbers coming from? 64, 49, 81. But why am I using those particular ones? Why didn't I use things like 10, 20, 30? Why am I using 4, 9, 16, 25? Think outside of the realm of statistics for a second. What's special about the numbers 4?
Oh,
No.
it's 2 times 2 and like
It's
3
2 times 2 and 3 times 3 and 4 times 4. Did you catch what you guys said? This is a half of that, and a half is 1 over the square root of that. This was a third of that, and this 1/3 is 1 over the square root of 9. 1 over the square root of 16. 1 over the square root of 25. It's quantifiable because it's predictable. It's following the sample size. As the sample size goes up, the deviation is going down, but it's going down as a function of the sample size. Hell yeah! That lets us quantify, okay, if I want to be within 2%, what size of a sample do I need? You now have an answer to that. Yay! It's called the power of hypothesis test. You guys ever have a Stephanie Howe for HHP class here at COCC? Working on her PhD right now, and it has this very question. I got to do the power of my test. Let's sit down and talk Excel and talk curves. Boom, done. Totally rad. This is how you answer that question. This is how you decide on a sample size. How big a sample do I need to be within 2%? This helps you answer the question. Rad. Fair? You're not quite as slight as I am, it's okay. It's understandable.
Regurgitate that, that's really cool.
Say that again?
I couldn't regurgitate.
You don't have to regurgitate it. You don't have to regurgitate. Let's synopsize instead of regurgitate. Okay? I don't want you to regurgitate anything, but I do want you to, let me put it all together for you here. This is called, friends, the mighty central limit theorem. Please don't write this down. I will have this for you online soon. If the server's not up, I'll email it to you so you have it. Okay? What I want to do in these next 6 slides, essentially, is just recap what you just discovered for yourselves. So the problem, you want to study a population. Of course you do. You always want to study a population. But you can't get the population, so you get a sample of the population. That's the whole point. So you want to know what the average is most likely. You might even want to know what the standard deviation is. But the best you can do is get a sample. Let's call the sample a size n. Now we had a bunch of different n's. We had 4, we had 9, we had 16, we had 25. We had different numbers. But in n, general, it's just n. Okay, this is the first part of the mighty central limit theorem. And you guys figured this out within 2 minutes. Number 1, the sampling distribution is going to be normal. Yay. You get a bell curve. Why are we happy about that? Because it's easy because you know stuff about the bell curve. You don't know stuff about trimodal distributions or highly left skewed distributions or whatever the other ones were, the flip of the bird distribution. But you know lots about the normal distribution, 68, 95, 99. 95% is 1.28. That's the 90th percentile z-score. We know all kinds of stuff about the normal distribution. Yay. So that's good. Even more yay-ish, yay squared, is the fact that it's centered on the average. So you don't know what the average is, but you know the distribution is actually centered on it. And what that means numerically, I made this up, I hope you don't mind. I took all of the x bars and averaged them, and the average of all the x bar averages is actually equal to mu. I want you to understand the significance of that equal sign. This is not an approximately equals. This is a literal equal sign. Mathematically, say that again, Corey?
Not an ish.
This is not an ish. This is an exactly equals. This is crazy to think about, friends. Very rarely in this class do I ever say, this is equal to this. This is equal to this. Now here's the problem with that statement. That statement's great, except it's a little bit practically useless. Because your individual sample average is probably not equal to mu. We saw that already, correct? Like on the blue graph over there. 33% were close, within half or within 1 unit of the average, but then 33 were above and 33 were below. So yes, on average they equal, but the individual ones don't. So, what do we then apply? Corey already said it. What do you apply when you can't get something exact? It's a 3-letter word, starting with I, ending with sh. You have to put an ish on there, don't you?
Yeah.
That's the whole point of ish. Ish gets you close, and then an up and a down, and you're somewhere in there. Let's quantify the somewhere in there right now. Okay? That's the whole point. You have to figure out the standard deviation of your sampling distribution. That's the whole point. This was what we spent the past 15 minutes talking about. Now, just so you know, that sample standard deviation of that distribution is very often called the standard error of the mean. It's called, you probably have heard this term before. Those of you who've heard it before, Michael, absolutely. Those of you in psych and soc and early childhood ed, you'll definitely be hearing this term. It's very often in research journals. The only difference between the standard error of the sampling distribution, or the standard error of the mean, and a sample standard deviation is the use of it. The sample standard deviation is purely descriptive, purely. In other words, you take a data set and you report back what S is. What the standard error is it's an inferential measure. It allows you to predict out into your population. So for example, you want to say 68% of the time, I'm fairly sure that my average is between blah and blah. My average in the population, you need to use the sampling standard, the sampling error, the standard error of the sampling distribution. That's what you have, and you'll see it, what I'm talking about here momentarily. So basically, this is the correction that you use. This is the correction to account for step 2, which was that your average is not mu. What you do is you fix, you ish the average by slapping one of these, or say 2 of these, which is the standard, because 2 errors will give you what percent of the area? 95. Two of them gives you 95, right? One of them gives you 68, for sure. But the standard is 95% by going out 2. So here, this looks vomit-inducing. But process what it means, and it's not vomit-inducing at all. What is X bar plus 2 of those standard errors? What would that be? What's your X bar again? Remind me what X bar is. It's your sample average plus 2